Hello everyone, this is chapter 2.3 where we'll be discussing calculating limits using limit laws. Now limit laws are really just properties regarding limits, and there's actually a total of 11 in the book list, and here are just the first 5. So I say here if c is a constant and the limit of f of x and limit of g of x as x approaches a both exist, then we can say the following. The limit of the sum is the sum of the limits, limit of the difference is the difference of the limits. The limit of a constant multiple of one of the functions is that constant times the limit of that function. The limit of the product is the product of the limits. And the limit of the quotient of f of x and g of x is the quotient of the limits of those functions. Of course, here the division only really holds when the denominators are non-zero. So here we're assuming the g of x is not the zero function, and moreover, the limit as x goes to a of g of x is non-zero. Good. So now I'm going to actually not do an example directly, but or at least not right away, but I'm going to show you the rest of the total 11 limit laws. So let's take a look at the other 6 right now. Right, so as promised, here are the other 6. So I've added some things here. So notice I say if c is a constant, n is a positive integer, and then the limits like we had before exist, then the following are true. So 6 says that the limit of a power, positive integer power of f of x is equal to the power of the limit. Now, by the way, positive integer just means positive whole number. The word integer means positive, negative, or 0 whole numbers. So no fractions, basically. I mean, well, 3 is technically a fraction. When I say fraction, I mean like something where the denominator isn't 1. But, you get the idea, hopefully. Now, 7 and 8 are kind of no-brainers. 7 says the limit as x goes to a of a constant is just equal to the constant itself, which makes sense because since the expression c has no x in it, and c is a constant by itself, as x approaches any number, any value, doesn't really matter because c is independent of x. So for instance, what's the limit as x goes to 10 of the number 3? Doesn't really make sense because 3 is independent of x already. So 3 will always be 3 no matter what. That's kind of what 7 says. 8 says as x goes to a, the limit is equal to a of x. So basically this says as x goes to a, x goes to a. So not quite in the same range as far as simplicity, but they're pretty similar. Okay, 9 actually combines 6 and 8. So this basically says that when the function is equal to x, then this approaches a to the n because the limit as x goes to a of x is just a itself. So this is really a combination of 6 and 8. And 10 kind of says the same thing that 9 does, only with roots. But notice here n is a positive whole number root. Okay, good. 10 also tries to do the same thing as far as what 6 does, only with roots. But here, we assume that f of x is positive when n is even, which makes sense because otherwise when you have an even root, you can't have a negative inside the limit. And we assume the limit is also approaching, so maybe I should say that specifically we're assuming the limit as x goes to a of f of x. We're assuming that limit is positive, otherwise we can't do anything there. Good, but I mean it kind of makes sense because otherwise f of x, or at least the nth root of f of x if n is even, won't ever make sense if f of x is negative. So we're assuming kind of f of x attains only positive numbers, so the limit should be positive as well. But anyways, I'm just kind of throwing that out there. Now, after discussing these, so next what we're going to do is I'm actually going to do a problem that will use limit laws. It's not the funnest thing in the world. It's honestly a little, I don't want to say degrading, but it's fairly obvious. But at least we see the use of the limit laws and we know that they're true, and I've listed them out here so that we can see that they are indeed a thing. And, for whatever reason, label this as 10, that was 11. So otherwise there'd be 2 10s. Okay, good. So after that, we're not quite done yet though, because even though 2.3 is basically entitled limit laws, we're going to go a little beyond that and see things that we kind of saw already, but in a more general context, and we'll even develop new tools that'll help us find limits where we couldn't have before. All right, so let's see if we can tackle this limit using limit laws. So the first thing I'm going to do is use that law that says that the limit of a quotient is the quotient of the limits, and this is as x goes to -2. So we're going to split this up basically. So this is f of x over g of x, so this is the limit of the top one, divided by the limit of the bottom one. So imagine these limits are in parentheses like this, just so we can kind of see that more in detail. Good. And now in each one of these, we're going to actually split things up, again using limit laws. So I'm going to take the limit of each term of this numerator using essentially the addition and subtraction limit laws. So there's going to be limit as x goes to -2 of x to the third plus limit as x goes to -2 of 2x squared minus limit as x goes to -2 of 1. The denominator is going to be limit as x goes to -2 of 5 minus limit as x goes to -2 of 3x. All right, so there are a few things I want to do here. And again, you can kind of see that really we should just be plugging the number in directly. And that's kind of what I'm going to describe in a second, even though we've kind of seen it already in a previous section. So the first thing I want to do before we get to that point is I actually want to use more limit laws, but I don't have too much space here. So I'm going to do the following. I'm going to notice that this is a constant times x squared, this is a constant times x. So we saw that there's actually a limit law where you can pull out a constant multiple. So this 2, I'm actually going to pull out in front of the limit as a multiplier. Same thing with this 3, it's a constant, so we're going to bring it outside of the limit. And that's just using that limit law. Now we're set. Now we can use, again, some more limit laws, but it'll be more like plugging in now. Because now we only have powers of x, basically, and constants, of course. So we can see that this first limit is just going to be -2 to the third. This is going to be plus 2 times -2 squared. And then this, of course, is just going to be 1, because 1's a constant, so no matter what x is, this number 1 is still 1. Similarly here, this is 5, and then -3 times, as x goes to -2, x is equal to -2. And now we can clearly see, really what we have here is just this same exact thing we had here, but just plugging in directly. So now I'm going to actually do it and see what we get. We get -8 plus, that's going to be 2 times -2 squared is positive 4, so that's also 8 minus 1. So those cancel, so we just get -1 on top. This is going to be 5 plus 6, so that's -1 over 11 is what I'm getting here. Okay. And now, again, this direct substitution property, otherwise known as DSP, I introduced kind of early on in 2.2, earlier than I should have introduced it. But at least it kind of gives us an idea as far as how limits really behave. We're trying to plug in the number. If you can plug it in, plug it in. That's basically what this is. We actually saw a counterexample to that idea, and that is actually with piecewise defined functions, where if you plug it in directly, you may get something that actually is not being approached as far as limits go. So here, this is actually a very specific version of DSP, and it says that if f of x is a polynomial or a rational function, and a is in the domain of f, meaning we don't get any zero denominators or any undefined number like that, then the limit as x goes to a of f of x is just f of a. So in other words, just plug it in. So this basically says that if you can plug it in, the limit, the thing we're approaching, and that's your answer. Now, really it only says it works if you have a polynomial, so a sum of powers of x, or a rational function. A rational function, by the way, is something like this, where it is a quotient of polynomials. Now, to be quite honest, DSP actually works for a bunch of other different types of functions, but the names of those functions are kind of hard to categorize them, basically. I really want to say it works for any non-piecewise defined function, but that gets a little iffy because, in some eyes, every function can be defined as a piecewise defined function. So it's just a little specific. So anyways, so now we're going to discuss something else, and we'll actually be able to develop, again, more tools as far as how we can solve limits that we weren't really able to do otherwise. So let's take a look at those examples right now. Right, so this is one of the tools I was describing earlier. Here I say if g of x and f of x are equal to each other when x is not equal to a, then the limit as x approaches a of g of x and the limit as x approaches a of f of x must be the same as well. So basically, if we have two functions that are the same, except for at one particular point, at the point a, then their limits are the same, because if it's true for all values except for a, then it's true for values around a. So as you approach a, for each of them, you'll get the same limit. So we actually saw an example of this when we considered this function that looked something like this, where as we approached a, we got a certain y value. So let's call that y value L. So let me create a y-axis here. Looks okay, I guess. So notice as you approach a from the left or from the right of this function, we get a. So let's call this function f, for instance. But now let's say g is the same function, but let's make it a piecewise function where at a, we have this value here, which is not equal to L. So of course, f and g are different functions. They're equal to each other except at a, but notice as you approach a for each of them, you still get the same limit. So we saw an idea kind of similar to that, but here it's just worded kind of in general. So how I'm going to use that here for these examples is I'm basically going to, well, apply some algebraic manipulations, and that's what this actually allows us to do. So I'm going to manipulate this expression so that it looks like a different expression. Basically, I'm going to cancel out the denominator because that's what gives us problems here. Notice when we plug in 0 directly, we get 3 squared, which is 9, minus 9, so that's 0, over the denominator will be 0 too. So we get 0 over 0, which I described earlier as being an indeterminate form. And I said, this is in chapter 2.2 by the way, that when you have an indeterminate form, go back, try to manipulate things and cancel out, and then if the denominator is canceled, then you can try DSP again, and then hopefully you get an actual value. And there's a similar story going on here. But let's see if we can see what happens. So what I'm going to do is I'm going to still be in the limit here, but I'm going to try to expand things out and manipulate the inside expression as much as I can. Let me kind of erase this for room so that the denominator hopefully goes away. So notice on top, if you expand 3 plus h squared out, you'll get 9 plus 6h plus h squared. And this is of course because 3 plus h squared is 3 plus h times itself. So you have to FOIL that out. You end up getting the first one squared plus 2 times the product, so that's 6h, plus the last one squared. And that's just a common binomial expansion for the second power. Here the 9's cancel, we're still over h. But now notice what happens is that at the top, the two terms we have left over now, both contain h. So we can actually factor that out from the numerator. So we're still in the limit as h goes to 0 of the top over h. Now you'd expect me to write 6h plus h squared, but I'm actually going to not waste too much time here. And notice what we have left over. They both have h in common. If you pull h out, you'll have 6 plus h left over. And now we can actually cancel these h's out. The only issue is that you actually can't cancel them out when they're equal to 0, but h can't be 0 anyways because you'd be equal to 0. So really what we end up getting is this, the limit as h goes to 0 of 6 plus h after cancellation. So notice, these expressions are kind of the same but kind of different. In the sense that if you graph them, the graphs will look the same except for at the point 0, because we've canceled out where it's equal to 0. Here, this expression exists at 0. Here, this expression does not exist at 0. But again, we were able to kind of finagle things, so to speak, so that we have no problem now here. So now we can apply DSP. and we get 6 plus 0, which is just 6. And again, since these expressions are the same except for at 0, well, we can apply this tool here to say that these are legitimately the same limit. So the limit of this is 6, the limit of this is 6. So again, this statement really just allows us to do algebraic manipulations. Now, this problem we actually saw before in 2.2, and we agreed the answer was 1/6, but that was just by plugging in numbers. So now I'm going to show you how to do this with algebraic manipulations. And this works anytime you have an expression that involves a radical and either minus a number or plus a number. Even if it's a sum or difference of two radicals, if you have an expression where one term is a radical, you can always do the following. We're going to so-called rationalize the numerator. So I'm going to multiply top and bottom by the conjugate of the numerator, of the expression containing the radical. So now, what is the conjugate of an expression? So the conjugate of a rational expression is the same expression, but with a sign change of the two terms. So instead of radical t squared plus 9 minus 3, we're going to write radical t squared plus 9 plus 3. Why on earth would we do this? Well, of course, we're doing this to force a difference of squares. A difference of squares in the top will now no longer contain a radical because we'll be squaring terms. So now we'll have the limit as as t goes to 0 of, the denominator now will be t squared times this conjugate expression. I'll actually leave it like that. We could distribute it if you like, but you'll find out it's best to leave it like this actually. And the reason why it's not too hard to see, notice our problem here was h, but we manipulated things so the h is canceled. So our goal here is to manipulate things so the t squared cancels, hopefully. So notice having t squared pulled out in the bottom to prepare it for cancellation is a good idea. So if we distribute it, we lose that preparedness, so to speak, to be canceled. Now on the top, again, we get a difference of squares. So if you treat this as a minus b times a plus b, that always foils as a squared minus b squared because of the difference of squares. So the radical squared cancels the radical and you just get t squared plus 9. And you can FOIL it out on your own if you'd like to see that, but that's indeed the case. And minus b squared, which in this case is 3 squared, which is 9. Perfect. So now what do you notice happens? Well, you notice that these 9s definitely cancel out. So we end up getting t squared over this, but then the t squares cancel. So just so I'm not being super sloppy, I'm going to write it, even though we can kind of see it already. So as t goes to 0 of t squared over t squared times that conjugate quantity, t squared plus 9 plus 3. So now here the t squares cancel, so we get 1 left over on the top, because the top is 1 times t squared. Perfect. Now this is the limit as t goes to 0 of 1 over radical t squared plus 9 plus 3. Now again, this expression here and the original expression here are not the same. This is valid when t is equal to 0. This is not valid when t is equal to 0. But they're the same otherwise, so we can use this tool here. And plugging in 0, what do you notice we get? We get, using DSP, 1 over the square root of 9 plus 3. Because as t goes to 0, t squared is 0. So we end up getting radical 9 plus 3 in the denominator, which is 3 plus 3 in the denominator, which is indeed that 1 over 6 that we got by plugging in numbers. But now we see it algebraically with no calculators at all, which is fantastic. All right, great. So now we're going to continue our path on kind of developing more of these tools, and we'll see some that are even crazier than the one here. This one actually isn't even that crazy. So we'll take a look at some of those right now. All right, so this tool here, limit laws are also valid for one-sided limits, will help us hopefully understand and be able to solve limits that involve essentially piecewise defined functions. Now notice the absolute value of x. What does the absolute value of x do? Well, when x is negative, to remove the negative symbol, when x is positive, that's the actual number. So the absolute value of 10 is 10, the absolute value of negative 10 is 10. So remove any sign, if any. But we can actually write this as a piecewise defined function because we have these two what-if scenarios. So if x is positive, then the absolute value of x is that number itself. But if x is negative, well, then you remove the negative, and one way to do that is by multiplying by negative, it makes it positive. And when x is 0, the absolute value of 0 is 0, so we can put an equality in, let's say, this one, and that works out. So absolute value of x really is a piecewise defined function. So to find out if this limit exists, we must see if the limit exists on each side. So notice when we kind of split up into the two-sided limits, so I want these two limits to be the same. So I'm not saying this is equal to this, but I want to consider this. So let me just kind of put an implication arrow here. So let's consider the right and left-sided limits and see what happens. Now, the interesting thing here is that if we consider the right-sided limit only, then here we're only plugging in numbers that are bigger than 0. And when x is bigger than 0, we're using the top definition of this piecewise defined function. So this is actually, believe it or not, equal to the limit as x goes to 0 from the right of x itself, because absolute value of x is equal to x when x achieves positive numbers. And that, of course, is equal to 0. So I'm kind of getting in the way of this piecewise defined part. Let me kind of lower that, I guess. X is bigger than or equal to 0, and then if x is less than 0, that's okay. Okay, perfect. Just get rid of that. Okay, good. Now here, something kind of different happens. When x is to the right of 0, to the left of 0, when x is approaching 0 from the left, then that means we're less than 0. We're plugging in numbers that are less than 0, so we can use the bottom definition here. So that we have now the limit as x goes to 0 from the left of negative x, because absolute value of x is negative x when x is approached from the left, when we're plugging in numbers less than 0. So notice this is just negative 0 by DSP, which is also 0. Since these two agree and are equal, we're in a good scenario, because that means this limit is the same as that, and in fact is 0. So this implies that this limit is equal to 0. Perfect. Now on the other hand, something kind of different and funny happens when you have something like this. So the limit as x goes to 0 of absolute value of x over x, well, let's see. So we want to check out the limits from the left and from the right. So let's consider the limit from the right first. So notice from the right, well, this just becomes x over x, because absolute value of x is equal to x when x is achieving positive numbers. So I'm going to skip this middle step here and just replace absolute value of x outright with x itself. That x on the bottom stays x. So notice this reduces to 1, so this is actually equal to 1, because it reduces before we can plug in the limit. Or we can do that algebraic manipulation I was talking about previously. So here we get 1. Okay. Let me not box that actually. But we get 1. All right, cool. What about from the left though? Well, as x approaches 0 from the left, absolute value of x would be equal to negative x, because again, when the absolute value of x, when we're plugging in negative numbers, that is, to the absolute value of x, it's equivalent to plugging them into negative that number. Negative of those numbers that are less than 0, basically. But notice here, negative x over x, and remember the denominator is still just x, that doesn't change. This reduces to negative 1, and then that's a constant, and that in the limit is negative 1. And there's an issue here because in this case, these are not equal, so that's kind of a sad scenario in the sense that the limit actually does not exist, because each of the one set of limits approach different things. All right. So now last example here, for this discussion anyways. I'm still going to talk more as far as 2.3 goes. We want to consider the left and right limits about 4. So let's take a look at the left limit here of f of x. And the left limit means, again, we're approaching numbers that are less than 4. And notice this piecewise defined function isn't even isn't even valid at 4 because there's no equality like there was here in this piecewise defined function. So the domain of this appears to be everything that is, everything that's not equal to 4, it would be the domain of this function. But in any event, when we plug in numbers that are less than 4, we're only using the bottom one. So this becomes a limit as x approaches 4 on the left of the expression a minus 2x, because f of x is equal to that when x is approaching 4 from the left. And notice when you try DSP here, what do we get? We get 8 minus 2 times 4 is also 8. So we get a minus 8 using DSP, which is 0. From the right, though, let's see what we get. Well, from the right, the limit as x goes to 4 from the right of f of x is equal to the limit as x goes to 4 from the right of, well, again, when we're approaching 4 from the right, we're plugging in numbers that are bigger than 4. And if x is bigger than 4, then we use f of x to be equal to the top expression, radical x minus 4. And then now using DSP, we can plug in 4 directly, even though we're approaching from the right. So this is an x. So we'll get radical 4 minus 4, which is radical 0, which is of course 0 as well. And again, since these both are the same, since they're equal, that makes us happy because that means that that is actually the answer to this two-sided limit. So that implies that the answer is both of these, which is 0 itself. Let me box that better. So the answer is 0. Perfect. So now we're going to look at one more tool and see a few examples of that. Right, so this is the last thing finally to discuss in 2.3, and it actually has a name now. This is called the Squeeze Theorem. It's a pretty important theorem in limits. And it basically says that if you have this three-part inequality, f of x less than g of x less than or equal to h of x, when x is near a or except possibly at a, and the limit of f is equal to the limit of h as x approaches a, and let's say that's equal to L, then the limit as x approaches g of x must also be equal to L. So really what this says is that if you have this three-part inequality, and I'm going to rewrite it over here just to kind of show some visualization. And we know that the limit of the outer two approach a number L. Then what this means is that the limit as to these arrows are as x goes to a, it's kind of what we're doing. So these arrows again are kind of approaching, so they basically describe limit. So then that means that the limit as g of x, as x goes to a of g of x, must be some number that's also in between L. So this will approach this in the limit. But that means that this inner limit here is kind of squeezed, hence the name, in between these two that are the same limit. So that implies that the limit as x goes to a of g of x must be equal to those numbers, which are the same number. Okay, so I'm going to try to use that to solve this pretty difficult otherwise limit. And it's a little funny because here we actually can use a multiplication law, and let me kind of explain why. So why can't we just say, oh, it's just this times the limit as x goes to 0 of the other one? Well, the reason is actually kind of simple. So limit laws only really work when the limits exist. Here, this limit exists, it's just 0. Here, this limit doesn't exist. Because though sine is okay, we're doing sine of 1 over x, and as x goes to 0, that's sine of 1 over 0. And I guess you can argue that that approaches positive or negative infinity, but what's sine of positive or negative infinity? You can think about it, but you're not going to like the answer. It doesn't exist. So instead of doing it that way, which we can't do it that way anyways, we're going to apply the Squeeze Theorem. Now, how do we do that? Well, in particular, the Squeeze Theorem is generally used when you have something that naturally has an inequality like nature to it, like sine, for instance. And what I really mean by that is that if you graph y equals sine of x, it looks like this. So namely, the highest it can be is 1, the lowest it can be is negative 1. So it's so-called bounded between 1 and negative 1. That's the largest it can be, and this is the smallest it can be. So with that being said, we know that sine is in between negative 1 and 1. Similarly for cosine, but not for tangent. Tangent, remember, this graph has those asymptotes, so it can actually go as high as positive infinity and even as low as negative infinity. But sine and cosine are definitely bounded between negative 1 and 1. So with that being said, we can multiply both sides of this by x squared. And in fact, you know what? Let me say the following. This is true for any value of sine, sine of anything. So I'm going to say here sine of theta, so I don't get confused. This even works when theta is equal to 1 over x, let's say. So sine of 1 over x, the largest it can be is 1, the smallest it can be is negative 1. So for that reason, x squared times sine of 1 over x must be in between what? It must be in between 1 times x squared, which is x squared. Let me kind of erase this a little bit. And negative 1 times x squared, which is negative x squared. Now again, if we didn't have that x squared part, then sine of 1 over x would be in between negative 1 and 1. But then multiplying through by x squared, we get this 3-part inequality, which is true for all values of x actually, believe it or not. And then if we take the limit of each of them, we'll notice the outer two approach 0 in the limit. So what does that mean? That means the limit as x goes to 0 of x squared times sine of 1 over x has to be less than or equal to 0 and bigger than or equal to 0 as well. So this implies by the Squeeze Theorem that the limit is equal to 0. Awesome. Great, so that was a really good example of the Squeeze Theorem. That's the only example I'm going to do actually. I don't want this video to be too long. It's probably pretty long already as is. And I'll see you in the next videos for 2.4 and beyond. Thanks for watching. Hope you enjoyed. See you then.